We're going to look at Charles's law, which is a relationship between the temperature and the volume of a gas. And we talked about another gas law previously called Boyle's law. Boyle's law is a relationship between the pressure and the volume. But Charles' law was described by somebody named Jacques Charles. And actually, Charles is his last name. And there's a relationship between the temperature and the volume of a gas. So we're going to look a little bit more closely, especially with the properties that are related to gases. If you remember, the gas properties are generally accepted as pressure and volume and temperature, and then moles. So the moles is N for number of particles. But we talked about Boyle's law being pressure times volume here. Okay, so we have the first conditions, P1 and V1, and then second conditions after we did something to the gas, whether we change its pressure or its volume. Okay. Charles's law here, though, is a relationship between the volume and the temperature. Okay, and you'll see the proportion is different. This time it's not multiplying, but it's dividing. So V1 over T1 equals V2 over T2 is a law. It's written as a calculation or an equation, but it's actually the law. So let's assume we have this situation here where we take this piston here. And so this is basically a syringe, and you could find these at the store, for example, at a Tractor Supply company or something, a syringe for dispensing medicine to animals, or even if you've ever had your tooth removed, they'll give you something like this so you can use water to clean the area where the tooth was. As gross as that is, that's what this is. So this part is called the piston, and it's the long stick. This is a gasket, if you will. And then this big chamber here is part of the whole setup. Okay. So if we assume that we have a gas at room temperature, 20 degrees is often accepted as room temperature, and we submerge this into a beaker of boiling water, 100 degrees Celsius. We put it in a beaker of boiling water because that way it's consistent rather than just heating up the sides of it with a Bunsen burner, for example. If we submerge that, then we could say, well, the temperature goes from 20 to 100 degrees. And we might say, well, that looks like it gets 5 times hotter. That's not really what works, but let's assume that it does. Charles's law would show us that the original gas here, the volume, expands 5 times its original size. We're going to find out that that doesn't really happen, and we'll show you how in a minute. But these dots here represent the gas particles. Now, actually, there's more than 6. There should be something like 6 times 10 to the 22nd or even 23rd particles in there, right? A mole of gas. And so we're just showing dots here to represent that as the particles get hotter, they bounce off of each other more energetically. They bounce off the walls of the container. So that's why we get a bigger volume, is because they're bouncing off of each other and it takes up more space. So let's try this out with a balloon before we go back to this idea of the piston chamber here. If we take a balloon here and we call it 2,000 mLs, right? That's about the size of a 2-liter bottle. And we're going to call it 20 degrees because, like we said, that's room temperature. And we stick it in the freezer, right? Because that's what you do. You stick it in the freezer. Well, a freezer can get not only to 0 degrees Celsius, but in fact, it could get colder, like negative 10 degrees Celsius. So we kind of assume, based on our experiences, that a balloon that gets colder would shrink. Okay. How much would it shrink? Well, that's what we're going to find out. If we shrink it down to 0 degrees, or if we put it in the freezer for long enough, it gets down to negative 10 degrees. What actually happens to the volume of the balloon? We can first look at what happens to the volume, but I want you to do this. From now on, when you are solving calculations in chemistry or physics, you write down the original form of the equation, and then you isolate the variable. You solve for the variable first before you start substituting numbers. In this case, we are looking for the final volume, right? What's that new volume going to be? T2 is a denominator here on this side of the equal. But if we put it on the other side of the equal sign, then it becomes a multiplier. So the equation becomes this. Now I put the V2 on the left side of the equation because that's normally how you do it, right? V1 stayed in place. But then I put this temperature ratio in orange. I put them in parentheses, okay? And there's a reason why. I want you to start to see that this ratio is very helpful. And if you are going to take the ACT, then you're going to want to know this because this helps you go faster. Something about knowing this ratio is going to help you. But here's where it's getting interesting. So here's the 2000 ml, 2-liter size of balloon. But the second temperature we said was 0 degrees Celsius, right? That's a colder temperature. If we do this, then it looks like the volume of the gas is 0. In other words, if we cool this gas down to 0 degrees Celsius by putting it in a freezer, it looks like the balloon disappears. That doesn't really happen, but that'd be a great idea because that way we could take pollution, for example. We could put carbon dioxide in a balloon. We could then stick it in the refrigerator or the freezer, and we could actually make it disappear. I don't suggest you try this at home, and if you do, just don't tell your neighbors what you're up to. But go ahead, take a balloon, stick it in the freezer, and see what happens. Maybe it'll disappear. We get even more interesting results if we try the calculations with negative 10 degrees, because freezers do get down to negative 10 degrees. If we use our calculations and we substitute and we did everything correctly, it turns out that the new volume of the balloon would actually be negative 1,000 milliliters. Now, what that means is we stick the balloon in the freezer, we wait a while, it gets down to negative 10 degrees, and not only does the balloon disappear, but the space where the balloon was has sucked up 1,000 mLs of the surrounding environment. So by putting a balloon in the freezer, we've actually made the freezer smaller. So again, you can try this if you like. The reality is it doesn't work like that, but you're more than welcome to try it, okay? What we have to look at is this concept of the Kelvin scale. It turns out that the temperature scales that we use don't work. Now, they work for certain things that we do in chemistry, but it doesn't work for gas laws. And so let's take a look at that. First of all, let's talk about these physical properties of water when water boils and water freezes. If we use the Fahrenheit scale, and that one's been around for a while, Fahrenheit, for some reason, said that water freezes at 32 degrees or marks or calibrations. So he called it 32. And we know that water, if it's pure, is pretty consistent. And we know that it boils at the same conditions, okay? So we just assume that water boils under the same conditions. And Fahrenheit decided to call that 212. So now there's 180 spaces or degrees or graduations or calibrations between when water freezes and when water boils. But somebody else came along, and this scientist's name was Andreas Celsius, and he decided that water is going to be 0, which kind of makes sense, right? Let's call that the coldest that can get. But we also know that we can get colder than 0 degrees, right? 5 degrees below 0, for example. But he called it 0. The spacing between water freezing and water boiling is still the same amount of space, but Celsius called this 100 degrees. And it was also known as the centigrade scale. Centi meaning 100, grade meaning these little graduations or marks, right? And this 37 degrees here represents body temperature. Now, in the previous scale, the 98 degrees was proportionally exactly at the same spot. So for Celsius, we now have 100 spaces. But we saw here at 0 degrees that doesn't work if we're trying to talk about gas laws. It comes up with some nonsense answers like balloons disappear at 0 degrees and suck out the universe at negative 10 degrees. So we had to come up with something that worked. again, we have the water boiling here at this level and the water freezing at this level. And then this is our body temperature, proportionally speaking. This also has 100 spaces in between it, okay? Just like the other two scales, or at least the same amount of space. 100 spaces for Celsius, 180 for Fahrenheit. But this scale developed by a man named Lord Kelvin, he doesn't use the concept of degrees. He just called them kelvins for whatever reason. So we don't say 373 degrees Kelvin. We just say 373 kelvins. But no one's going to stop you if you say otherwise. All right. But where this used to be 0 for Celsius is now 273 because using gas laws, Kelvin found out, or Jacques Charles found out actually, that this 273.15 degrees below this is actually the coldest it can get. This is where a gas actually has a volume of 0. So we could actually do that if we were in school. We could actually do this lab. We could draw a graph that shows us that absolute 0 happens when a gas has 0 volume. So we're going to use this scale here called the Kelvin scale. Now the Kelvin scale works like this. If you have your temperature in degrees, like we did, 0 degrees, you add 273 degrees to it, okay? And that gives you your temperature, and you get this Kelvin temperature here. So if we had 20 degrees here, this would be 293, for example, in kelvins. And so what we're going to do from now on is not deal with Fahrenheit at all. That never shows up in gas law calculations. But if you have Celsius, what you're going to do is add 273. Technically, we should add 273.15. But right now, we're not going to focus too much on that. So let's go back to our original situations where we had a syringe and we had 30 mLs of a gas compressed in that syringe. That's from the original picture on the previous page. So there's 30 mLs of a gas. We say it was at 20 degrees Celsius. We now see that you can't really use 20 degrees Celsius because Celsius doesn't work. If you add 273, then you get this, 293 kelvins. Now, we might think, oh, to go from 20 degrees to 100 degrees means it gets 5 times as hot. That's not really what happens. Okay, it turns out we have to use the Kelvin scale. So this now becomes 393. And so now you can see that 293 up to 393 is not, in fact, 5 times as hot. If you remember, we're trying to find the new volume of the gas, right? After we heat it up, how big does that 30 ml size of gas expand? Here's what I want you to do. You always draw the original equation, and then you isolate the variable. So if you're looking for V2, leave the V2 right here, but we have to move the T2 out of the way. T2 is a denominator on this side of the equals, so that means it becomes a numerator when it crosses the equal sign. So you're left with this version of the equation. This is required, especially in college level work, when you solve your calculations. Now you'll see what I did here was I put the temperature ratio in black, and it's also set up aside so that it is in parentheses. And I want you to see that because that ratio is very important, okay? The new temperature, right? The boiling water temperature is 393. We used to call it 100, but it's really 393. And the room temperature gas was 293. Now, if I look at that, I don't really need a calculator to see that this is going to be a number greater than 1. So we could play with the numbers. We could put 39.3 over 29.3, right? That would still be the same ratio. That's about 40 over 30. If you just did this in your head, 40, that's like 4 over 3. And it's 1.33. The reason I'm telling you this is because when you do the ACT, that these questions have been known to show up, And you have to be able to do the math in your head to be quicker. Instead of using a calculator, you could eliminate half of the answers almost immediately by saying this ratio is greater than 1. Now, of course, you're going to use a calculator, but I want you to see that if on the ACT one of the selections is 40, for example, that means you know that options like 10 and 20 aren't going to be very useful for you because you know that the gas is going to get just a little bit bigger. Okay, so that's the concept of using this proportion here rather than using a calculator every time. Okay, so our gas in the original did not get 5 times bigger. It only got 1.33 times bigger. Okay, so let's take this balloon here and we'll call it 3,200 mLs. And let's say that it's about room temperature. We'll complicate it a little bit by calling this 222.7 or 222.7. And let's put it in the refrigerator. We now know that if we put it in the freezer, that it in fact doesn't disappear or in fact come up with a negative value, right? It actually will get smaller. So the question is now, how much smaller will it get? So let's assume this balloon is about, let's say it's bigger than a 2-liter bottle, right? We'll call it, just to keep it interesting, 3,200 mLs. And we may or may not have to get rid of the units, but these are equal, okay? Remember that if you have temperature in degrees Celsius, you have to add 273. And so now the temperature of the gas is really in Kelvin's 295.7. But if we put it in the refrigerator or the freezer, it doesn't get to negative 10, right? It's not going to be a negative temperature. It actually turns out to be, according to Lord Kelvin, 263 Kelvin. So now what happens is if we cool this gas from 295 to 263, well, as much as many of you would probably just say, hey, how can I just substitute the numbers and get the answer? Well, I'm trying to save you time by showing you what you should do if you have an ACT or a multiple choice exam, because these are going to happen. We know that if you take a gas, a balloon, and make it cooler, that the balloon's actually going to get smaller, right? So the way we think about it is these are the two temperatures that we had. Here's the cold temperature inside the freezer. This is room temperature, okay? Well, if we know it's going to get smaller because of the temperatures, all you have to do is take a ratio of those two temperatures, 263 over 295. And you can estimate, right? So I could take 263 over 297. What if I called this, instead of 300, let's just call it 30. We'll keep it simple, right? You could call that 29.7, which is really close to 30. And 26.3, you could call that 26.5. You know some number that's very closely related to this would be 27 over 30, right? 27 over 30 is about 90%. Okay, so this ratio here is just a little bit under 90%. Okay, so that's all I'm saying is that if you know the gas is going to get colder by these two temperatures, that tells you that the gas is going to be about 90% of the original size. If we do the regular setup then with Charles's law like this, we would see V1 over T1 and V2 over T2. So you're supposed to rearrange this equation, isolate the variable. That's the one you're looking for is V2. We saw that if you have T2 as a denominator, then it becomes a numerator when it crosses the equal sign. So you would get this set up right here. Now, if we do this without a calculator, we would see that, right? We said previously this 26.3 or 263 over 295.7, that's about 88%. When we do the calculation, it turns out it's 88.9%. But if you have a multiple choice, that's not going to make a big difference. If we call that 90%, that would be 10% off of this, okay? Now, I estimated at 2,900 milliliters, and it turns out to be 28 46. Okay? And so if we divided that, if we took the 2846 divided by 2900, it would be that we're about 98% correct. And so that's the basic idea of why we use these ratios. So that is Charles's law, the idea that a volume and a temperature here are related by this equation. And it's called the law because it always works. So we'll have more calculations for you later.